Good morning, ladies and gentlemen, and today we need to investigate different types of solutions that we might get when solving equations. So far, most of the work that we have done has given us kind of nice answers, and by kind of nice I mean integer solutions. We've seen answers such as x equals 3, we've seen x equals 8, we've seen x equals negative 15, but we haven't seen any partial values yet. So we need to understand that we can get some more complicated to interpret solutions to our equations and how we're going to describe them appropriately mathematically. In order to do that, we need to review the number sets that you've studied since as early as 5th grade and make sure that we're able to define them appropriately. Way back when you first started using numbers in school, in pre-K and kindergarten and 1st grade, you mostly talked about the natural of the counting numbers. The natural of the counting numbers considered numbers that you would naturally count with. They began at 1 and went up to positive infinity and didn't include any partial values, negatives, or 0. So the investigation of 0 is a really strange and interesting thing, and it wasn't invented too long after the natural and counting numbers were considered. That's funny because just last night my daughter had to describe what the digit was in the hundredths place for the number 67. And she was so confused. She came to me, she's like, "Dad, I don't see a number there." And she was right. There was no number. There were no hundredths in the number 67. So she was supposed to describe that place value as 0. That was kind of tricky for her to consider at first, but then she got it kind of right away once she recognized that there's a number that can represent nothing. When we expand the natural counting numbers to include the number 0, we have to redefine that set, and we give it a new name. We call it the whole numbers. And it's kind of easy to remember because the word whole has an O in it, which kind of looks like a 0. So the whole numbers include 0. Beyond that, you'd have to consider that, or the next logical space to have gone was that many people recognized that there weren't simply only positive numbers, but there were also negatives as well, representing owing money or digging down or temperatures below what we would consider 0. So the integers were created to represent the opposite of the whole numbers. The set of integers includes all the whole numbers, which start at 0 and go to infinity, and their opposites. There are no partial values when you're describing an integer. So if a question asks you to solve for an integer value, you should not get a decimal or fraction. That brings us to when we might start to talk about and think in terms of partial values, and we usually describe those quantities as rational. But you've got to be a little careful because rational, which typically means fractional, does include all the numbers we just described a moment ago, because the numbers we just described a moment ago, such as positive 3 from the integer, whole, and natural number sets, could be written as 3 over 1. Often when we're asking for a fractional solution, we typically mean a non-integer rational solution. So we typically mean some number a over b, where b is not 0 because anything divided by 0 is undefined. We'll talk about that later on. And b is also not typically 1 if we want a non-integer solution, because anything divided by 1 would be itself. So if you're looking for a non-integer rational solution, 4 would not be would not describe that possibility, because 4 over 1 would be equal to 1, and that is an integer. So if you're looking for a non-integer, you're looking for something like 3/4 as a possible solution. And we're going to start to see some more complicated to interpret answers that are going to be non-integer rational solutions. Rational means fractional, and technically it's going to mean a number that can be written in fraction form. So that will include the sets we just described a moment ago. The kind of the opposite of a rational would be an irrational solution. And irrational solutions or irrational numbers are numbers that are non-terminating and non-repeating decimals. So a non-terminating or a non-repeating decimal value is going to be difficult, or I should say impossible, to write as a fraction. A moment ago when I described rational numbers, I could have used 25 hundredths as an example. And 25 hundredths is really 25 over 100, a fraction. And if you really wanted to, you could simplify it by dividing out the greatest common factor of 25 and rewrite it in simplest form as just 1/4. My highlighter is going crazy. I'm not sure why, but I'm hoping that's not going to happen too often. An irrational number has a problem. It cannot be written as a fraction because it is a non-terminating, non-repeating decimal. The most popular irrational number that we often talk about is pi. Most people remember pi from previous years. And pi is typically 3.1415, I think 9, something like that, ... and the ellipsis means goes on forever and doesn't repeat. And if you actually went to your calculator and you typed in the value of pi, so I'll clear out my calculator, and if I do second and the pi key is above that little caret symbol, and I hit enter, your calculator will give you the first 10 decimal place values of pi. It will not go beyond that because it would take forever for it to literally take forever, because it goes on forever and doesn't repeat, for it to represent that. So it's rounding to the 10th place value there. But if you tried to write pi as a fraction, you might be able to understand what the difficulty might be. You could say, well, Tooch, isn't it 3 and 1/10? And I would argue, no, it's not 3 and 1/10 because there's another place value behind it. And you'd say, well, isn't it just 3 and 14/100ths? And again, I would say, nah, not really, because there's still another place value past the hundredths place value. So you might say, well, is it 3 and 141,000ths? And again, I would say, no, we're not there yet because we haven't identified the last place value. And the problem that you might suspect occurs with this is we can never identify the last place value because it goes on forever and doesn't repeat, and therefore we can never write it as a fraction. That's what happens with irrational quantities. There are a bunch of irrational quantities outside of pi. Anything that's not a perfect square would be an irrational quantity. So any number that's not the result of that number times itself, you cannot take the square root of. Some people get confused with the square root of 2 because they're like, hey, isn't 1 times 1 2? Which is a real weird thing to say because 1 times 1 is not 2. 1 times 1 is 1. But if you tried to take the square root of 2 on your calculator, what ends up happening is that you'll notice that it's a little bit less than 1.5. It just goes on forever and doesn't repeat. And that would be true of any number that's not a perfect square. Now, a perfect square such as 9, 9 is the result of 3 times 3. When you take the square root of it, your calculator says the square root of 9 is 3. So the square root of 9 is actually rational. It's not an irrational quantity. But it's important to know that that presents a problem. So if you took all the rational numbers, rational meaning fractional, they could be written in fractional form, and that's represented, or that you could identify that as a terminating or a repeating decimal. Oh, by the way, 0.333333333 should kind of look familiar to you. And that can be written as a fraction, believe it or not. 0.33333, if you trick your calculator and type in a bunch of decimal place values, and you do second math, just kidding. If you do math, it'll take you to the tab that can do some really useful processes for you, and the first of which is turn into a fraction. So if you hit enter for 0.33333, you trick your calculator into believing that it has a repeating decimal. It'll be like, oh yeah, that's 1/3. And you can do that for anything. If you did like 0.15151515 across your screen enough times, I forget what the actual number is, my kids have figured it out in the past, and you trick your calculator into believing you have that repeating decimal value, and you go to the math tab, select turn into a fraction, it will appropriately turn that into the fraction 5/33. Hopefully we'll get a chance to investigate that and show you why that happens later on in the year. It's not magic, there's actual mathematics behind it. It makes perfect sense. So if you take the rational and the irrational numbers and you put them together, you get what's called a real number set. And that's mostly what we work with in this class, real numbers. You start to leave the real number set when you try to identify the square root of a negative quantity, because the square root of a negative quantity is really awkward. Remember, square root says what amount times itself, so the square root of 9 says that 3 times itself would equal 9, so the square root of 9 is 3. But if you try and take the square root of a negative quantity, that gets really weird because you're asking what number times itself would equal a negative. And you guys are supposed to know this, that the only way to have a negative product is to multiply a positive times a negative in our mathematical system. And a positive times a negative would be negative, in fact, but it wouldn't be the same number times itself. So there is no way to get the same number times itself to equal a negative, unless you go into what we call the imaginary or the complex number system. So if you actually asked your calculator, hey calculator, what is the square root of -5? It's going to have an issue with that. When you hit enter, it's like, hey, there's no real solution. You see that up here? We're in real mode. All calculators must result in a real number. So it's having a problem identifying the square root of -5. We work mostly in the real number system. We've investigated the complex numbers in years past. I don't know if we're going to have enough time this year, but maybe. We'll see. It is important to understand that when you're trying to solve for non-integer rational solutions, fractional solutions, you can never have 0 in the denominator. 0 in the denominator is an awkward expression. So if you had 0 in the numerator, like say 0 divided by 5, that would ask how many times does 5 fit into 0. And you typed into your calculator as 0 divided by 5. And 0 divided by 5 is just 0. 5 doesn't fit into 0 at all. However, when you ask how many times does 0 divide into 5, you're asking the question, how much nothing can you fit inside of an amount? And that's really awkward because I don't know how much nothing you can fit inside of an amount. It would be like asking you how much nothing can you fit in your room, and you going outside to your front yard and coming back with nothing and putting it in there, and then going outside and coming back with nothing and putting it in there. And technically you could do that beyond infinitely. You could do that, to the end of time. So there is no way to describe that mathematically appropriate. And if you did that on your calculator, if you perform that computation and ask your calculator what is 5 divided by 0, it's going to have a really difficult time with that. It's like, I can't divide by 0. The number is indescribable. It's too large. So whenever you try and divide an amount by 0, we identify that it's undefined. There's no way to describe it. Okay, so as you get into the work down below, ladies and gentlemen, we're asking you to classify a number as a whole. We're asking you to classify the possible presentations or the expressions, the numerical expressions, as whole numbers. Which ones would be whole numbers? And for that, you just have to remember that the whole numbers start at 0 and go up to positive infinity. The whole numbers were created or observed after we had the natural, the counting numbers. We added 0, which is an incredibly important digit. So we're looking for any number from 0 to infinity with no partial values. Obviously, 8 would fit that description. Negative 5 would not. 12 thirds, if you simplify it on your calculator, comes out to 4. So that expression is a whole number in disguise. The square root of 14, if you attempted it in your calculator, 14 is not a perfect square. It's not the result of the same number times itself. It's funny because kids are like, yeah, 2 totally is, man. Isn't 2 times 7 14? Yeah, but 2 times 7 is not the same number times itself. It's 2 times 7. So if you ask your calculator what the square root of 14 is, you get this irrational quantity, and that is not a whole number. 29 sevenths, if you actually try to divide 29 by 7, hopefully you know that 29 is not a multiple of 7. So when you perform the division, you get a, that actually is a repeating decimal, 1428571, and then it's going to repeat on the back end. So that is clearly rational. Rational means fractional, but it is not a whole number. Square root of 9 is, that expression is really just 3 in disguise, and 3 is a whole number. And when you ask how many times does 6 go into 0, it goes in exactly 0 times, and 0 is a whole number. So our whole numbers should have been expressions A, C, F, and G. A, C, F, and G would have been choice 4. And I do want you to perform those computations on your calculator so you get more comfortable with the results of some of those more difficult to interpret relationships. Which amounts can be classified as integers? That requires you to remember that the integers are the whole numbers from above, starting at 0 and going on to infinity, and their opposites. The opposite of the whole numbers are the negative whole numbers. And that goes back to negative infinity. 1 and 2500ths clearly is not a whole number or its opposite because there's a partial value attached, so therefore it is not an integer. That would not be an integer solution. Negative 5 is the opposite of positive 5. That is an integer. When you ask your calculator how many times does 0 go into 13, it comes out as incalculable. That is undefined, and therefore that is not an integer. The square root of 25, that expression is just positive or negative 5 in disguise, and therefore it is an integer. The negative value of 32/4, so if you typed into your calculator negative, and you could use your fraction key, which is alpha F1, that's your shortcut. You could substitute in 32/4. So denominator really just means divide. 4 divides to 32 8 times, and the negative of 8 would be negative 8. So that too is an expression that represents an integer in disguise. Square root of 9 we already decided is 3, which is an integer. And negative 5 halves. So this is where a lot of students get confused. This is where they'll be like, Tooch, that's totally an integer, man. Watch me go. There's a negative sign there. Integer doesn't mean negative, guys. It means the whole numbers and their opposites. It could be a negative value so long as there's no partial value attached. And when you ask your calculator what is negative 5 divided by 2, the quotient is negative 2.5. And because there's a partial value there, that is not an integer. Now negative 7 dividing into 0, that's easy. Negative 7 doesn't fit into 0 at all. It has 0 value. If you typed it into your calculator, it would say 0, and therefore that is an integer. Our integers are B, D, E, and H. F, and H, choice 4. So in Roman numeral 3, we're asked to determine which amounts could be classified as rational, and we have to recall that rational means fractional, and that's not really a way to define a rational number. It's just a quick cheat to remind us what we're looking for, because we should know that rational numbers are any numbers that are represented as terminating decimals or repeating decimals. Apologize for the penmanship there. And what I mean by that is if you had, say, 25 hundredths, you're supposed to know that 25 hundredths is really 25 over 100. And that can be simplified to 1/4. And if you typed into your calculator 25 hundredths, and you went to your math key and asked to simplify that fraction, it would convert that to you to 1/4, because 25 out of 100, or 25 cents out of $1, is equal to 1/4. So similarly with a repeating decimal, if you were to do 0.333 repeating forever, you could trick your calculator into believing that it's observing that by putting a bunch of decimal threes into your screen and then going to math and turn it into a fraction, and your calculator say that's equal to 1/3. That's true of any repeating decimal. If you did say 0.151515 repeating long enough on your screen for your calculator to believe that it's a repeating value, and you went to math and you chose the first selection, turn it into a decimal, it would tell you that's equal to 5/33. It's not magic. There's a mathematical process to show that, and hopefully we'll get a chance to do that by the end of the year. It's really cool, actually, and there's some neat algebra involved. But the bottom line is that if we're trying to identify a rational number, something that can be written as a fraction, we need either a terminating decimal or a repeating decimal. The reminder that rational means fractional is that if we're dealing with any number that appears as a fraction, it must be rational, or any number we could write as a fraction. So in choice, or expression A, I should say, when we ask what would happen if you took any number and divided it into 0, any number would divide into 0 exactly 0 times, with the exception of 0. So for Roman numeral A, that could be equal to 0, and 0 could be written as a fraction by take any number and put it over 0, for instance 4. So A represents a rational expression. So does B, because B, -5, could be written as -5 over 1, and there it is in fraction form. It's technically a terminating decimal. It's -5.0, which fits both of our definitions, and B is rational. The opposite, or the negative, of the square root of 81, that's a little bit tricky because it's asking you to take the square root of 81 and then take the opposite of its value. If you type that into your calculator as the negative square root 81, your calculator says the square root of 81 is 9, and the opposite of positive 9 is -9. And -9 would be rational because you can write it as -9 over 1. Rational means fractional, any number that can be written as a fraction. Clearly, letter D is a fraction, -32/4, but if you simplified that and you divided 4 into 32, you're going to get -8. Whether the negative sign is in the numerator denominator are equivalent with the fraction bar, there's only one negative sign, which means you're going to take the opposite value of the operation once you perform it. So whether it's -32 divided by 4, or 32 divided by -4, or -32/4, they all equal -8. Letter E, be careful because that looks similar to letter A, or expression A, but it's not, because it's asking that ridiculous mathematical question, how much nothing can you fit inside any value, and that's indescribably large. It's almost beyond infinite, and that's going to be undefined, and that would not be a rational quantity. Square root of 9, we decided, is just the whole number 3, or the natural or counting number 3 in hiding, and 3 can be written as a fraction as 3 over 1, so the square root of 9 would be rational. -5/2 is clearly a fraction, therefore it must be rational, and if you convert it to a decimal, you get -2.5 if you actually perform that division, which is a terminating decimal quantity, and fits the definition of what it means to be rational. The square root of 20, there are kids who always say, hey, Tooch, man, I got this, watch me go. Square root of 20 is 10, because 2 times 10 is 20. Square root doesn't mean what number times 2 equals 20, it means what number times itself. And 20 is not a perfect square. There is no number times itself that's equivalent to it. It's a decimal value that goes on forever and does not repeat, and therefore it is irrational. So our rational values, if we were to list them, are going to be 0 divided by any quantity x. They're going to be -5. We'd also have to include the opposite of the square root of 81, -32/4, the square root of 9, -5/2, and that would complete the rational quantities from this particular set of numbers. When you flip, ladies and gentlemen, and you head on to the back, we now want you to use and apply those definitions that we just reviewed to evaluate some expressions. So when we evaluate expressions, we should be following order of operations, PEMDAS. We should actually go through the order of operations, evaluate any parentheses, and as you know, I think this should be GEMDAS because it should be any grouped quantity. There are other ways to group mathematical values other than parentheses. And then exponents, multiplication or division, and addition or subtraction. So in the first expression, we should evaluate the absolute value of 5 less 18. Absolute value is always, always, always positive. 5 less 18 is -13. Simplify the expression. Less 3 squared then actually take the absolute value of negative 13, which is positive 13, then subtract away 3 squared, which is 9, and the result should be 4, and that is in fact an integer. That can be done on your calculator. If you went to math, scroll to the second tab number, the very first selection is absolute value, and you could type in 5 less 18. You could scroll out of the absolute value bars. You could complete the expression by subtracting 3 squared, and we should get the same value that you and I just determined, 4. For letter B, we'd have to work inside the grouped quantity first, according to PEMDAS. We'd get 9. That should be multiplied by negative 3, and all that will be subtracted from 12 once we divide by 2. So as you're following order of operations, you've got some multiplication and division, and you should do the multiplication first, because in the expression it comes before the division, and that would require us multiplying 3 by 9 and getting 27. That's being subtracted from 12, and then ultimately divided by 2. 27 divided by 2 should be, that sounds like 13 and a half, and that's being subtracted from 12, and I believe we're going to get negative 1.5, and that is not an integer. Integers are the whole numbers and their opposites. They do not include partial values. So although expression A evaluates to be an integer, expression B does not. We could check that on our calculator. 12 less 3 times the grouped quantity 2 plus 7, and divided by 2. And hopefully we get the same value. That would indicate that we did it correctly, and we did. In expression C, when you evaluate a fraction, you're supposed to separate the numerator and denominator and evaluate them separately. You could put parentheses around them so you know which to do first. If you did the numerator, you'd have to begin inside the grouped quantity operation, and you'd have negative 4 times 2 doubled plus 38. Negative 4 doubled is negative 8, and negative 8 plus 38 would be 30. 30 divided by negative 6 should be negative 5, and negative 5 is in fact an integer. It is the opposite of the whole number positive 5. Integers are the whole numbers and their opposites. So we had two expressions that evaluate to be integer values. In Roman numeral 5, we've got to solve the equations and determine which of them would be non-integer rational solutions. Non-integer rational solutions, so rational means fractional, any number that can be written as a fraction, so that could include 5 over 1. But when we say non-integer, we mean you can't simplify it to equal the whole number or its opposite. There should be a partial value involved. So we're looking for answers that are like 5 divided by 2, or negative 3 divided by 8, or some fractional value with a denominator other than 1 when we simplify it. In the first relationship, we'd have to begin with distribution. In both expressions, we'd want to clear the parentheses, and when you take 7 times the quantity 4 plus x, you're going to get 28 plus 7x, and when you double the quantity x plus 2, you're going to get 2x plus 4. My preference is to transfer a variable at this point, use the additive property of equality to add the opposite of one of the variable terms to both expressions. That's going to allow it to cancel on one side and leave you with a two-step equation. From there, we typically like to reverse engineer the question, to go backwards through PEMDAS to undo the addition and subtraction, and we're left with 5x equals negative 24. Divide by 5, divide by 5, and your answer is x equals negative 24 fifths. I'm going to leave it that way because I kind of know what's going to happen here. When I divide negative 24 by 5, 5 doesn't divide into 24 without a remainder. Therefore, it's going to have a decimal value. It's negative 4 and 8 tenths. And that would be a non-integer rational solution. In relationship B, you'd collect like terms in the expression on the left. Technically, if we're in another country and we're showing all the steps so we actually become good mathematicians, we would use the commutative property of addition. To commute means to change position. And then we'd use the associative property to group the like terms, the variable quantities, together. And then we'd add them. I know that most of you all are in the habit of circling them. I at least like to underline them rather than circle them so I don't circle through an operation and make a mistake. We would then undo addition with subtraction, and we would divide out the coefficient of 5 using the multiplicative property of equality. You can multiply an equation by whatever you want, so long as you do equally on both sides, and we know that division is the same as multiplying by the reciprocal. So technically, when we solved 5x equals 45, we could have presented that as multiplying both expressions by 1/5. The denominator would indicate the division. 9 is a rational quantity because it can be written as a fraction. It can be written as 9 over 1. But we're looking for non-integer rational coefficients. So we're looking for solutions that have partial values. And this does not have that, so this does not solve in that manner. When you take a look at relationship C, my preference to begin to solve it, because I recognize that there are variable quantities in both expressions, would be to transfer the variable amounts. Careful not to confuse that with collecting like terms. Students sometimes do that. They'd be like, Tooch, I put the x's together. I got negative 2x. No good. Okay? You have to move or remove one of the variable amounts in either of the expressions by adding its opposite to both sides. I always prefer to add the opposite of the variable term with the lower coefficient. That's going to lead to working with less negative signs. So I'm going to add positive 4x to both expressions. I'm going to get 6x less 14 equals negative 22. I'm going to solve a two-step equation by adding 14 to both expressions. And I'm going to get 6x equals, if you're not sure what negative 22 plus 14 is, type it in your calculator, and you're going to get negative 8. You then have to divide both expressions by 6, and 6 doesn't go into 8 without a remainder or into negative 8, so you could leave your solution as negative 6/8. You're not wrong if you actually tried the division and did negative 8 divided by 6 and wrote your answer. Well, that would be tricky. My apologies. We don't like to write negative 1.3 with a bar of it repeating, even though it's mathematically correct. We start to try and work with more precision at this level of mathematics, so we prefer that you leave it as negative 6/8. Or if it's delta and it says write your answer in simplest form, you could recall the relationship, scroll back on your calculator, hit enter, it'll bring it back up, and then you could hit math, turn it into a fraction, and it will simplify that to negative 4/3. It simplifies it to negative 4/3 because it simply divides a GCF of 2 out of the numerator and denominator. 2 divided by itself is just 1, and anything divided by 1 is itself. So we're able to rewrite this as negative 4/3 equivalently. And that, in fact, is a non-integer rational solution. Which brings us to the essential question. This is the one you have to be able to do. This puts all the pieces of the puzzle from everything we've learned so far this year together in one question. Solve and check the following where x results in a negative rational non-integer value. All right, so clearly we're hoping for a negative sign. Rational means fractional. Non-integer means the denominator will not, so let's call this d for denominator, will not equal 1. So we're hoping for something like negative 3/7. When we go to solve, ladies and gentlemen, my preference is that you would put up a fence. You'd separate the expressions. My hope is that you would choose to double the denominator x plus 3. We like to clear parentheses or distribute whenever we're able to. And you'd rewrite the expression as 7/3 x plus 1 is equal to twice x plus 6 divided by 4 less 2. From there, what makes this difficult to solve is these fractional quantities in either of the expressions, or the fractional terms. So I'd like to get rid of them. And one of the fractional terms has a denominator of 3. We're dividing by 3. The other has a denominator of 4. You can multiply an equation by whatever you want, as long as you do equally on both sides, but you'd be really efficient if you chose to multiply by an amount that 3 and 4 divide into. So 3 and 4 divide into 12. They divide into, so the multiples of 4 are 8, 12, 16, 20, 24, and so forth. So 3 and 4 also divide into 24 and other values, and the lowest common multiple of 3 and 4 is 12. So the easiest way to solve this, or the most efficient way to solve this equation, would be to choose to multiply both expressions by 12. Now technically you could group the expressions on either side, and you could multiply by 12 and distribute it. But so long as you understand that multiplying both expressions by 12 or increasing them by a factor of 12 means that you're going to be multiplying the entire relationships by 12, you could simply show that you're going to multiply the terms by 12 without having to group them and then distribute as a second step. It could be a little tricky. My work could be a little neater, so it's going to be a little difficult for me to make sure I stay organized and not lose my place. 12 times 7 is 84, and you could divide 84 by 3 and then multiply by x, and that would be correct. But I prefer to simplify before I multiply. I prefer to divide 3 into itself once and into 12 4 times. And I'm left with 4 times 7 times x, which is 28x. technically divided by 1, but I'm not going to show that because anything divided by 1 is itself. And the most common error students make is they forget to multiply the constant by the coefficient of 12 or the distribution of 12. And the second in the expression on the right, I would choose to divide 4 into itself once and into 12 3 times. And then I would triple the numerator, multiply 2x plus 6 times 3, and the product would be 6x plus 18. And then once again, I have to make sure I multiply the constant in this expression by 12, and I get minus 24. We should then choose to collect like terms. Technically, we really just need to use the associative property of addition and group together 18 minus 24, thinking of it as 18 plus negative 24. You don't have to actually show that you're going to associate it. Most of us just underline it along with the operation and know that the operation is the sign of the number. And 18 minus 24 is going to be negative 6, or 6 being subtracted from 6x, equal to 28x plus 12. Once again, it's a little awkward because we have variables in both expressions, so I'm going to choose an appropriate method to transfer those variables. You're not wrong if you subtract 28x's from both expressions. That's mathematically correct. But I prefer to add the opposite of the variable term with the lower coefficient. So I'm going to subtract 6x's from both expressions. That's going to get me 22x's plus 12 equals negative 6. I'm solving a two-step equation. I would subtract 12 from both expressions. Or as I like to say, add the opposite. Subtraction is the same as adding the opposite. Positive 12 and negative 12 cancel. Any amount plus its additive inverse will always equal 0. I'm left with 22x in the expression on the left. In the expression on the right, negative 6 minus 12 more. If you're not sure, you go to your calculator. Negative 6 minus 12, if you chose to interpret it that way, is going to be negative 18. Or if you had negative 6 plus negative 18, negative plus a negative is just more negative. Haha. Let's do that the right way. How about this time we do negative 6 plus negative 12 so that we can assure that we get negative 18 as the same result we would have gotten had we subtracted 12 from negative 6. Negative 18. Divide out the coefficient of 22. And because 22 doesn't divide into 18 without a remainder, you could leave your answer as negative 18 20-seconds. But often we're asked to simplify that relationship. You could go to your calculator and type in negative 18 divided by 22, and you could select math, choice 1, simplify the fraction. It's going to divide out a GCF of 2, and it's going to say that the final answer should be that x is equal to negative 9/11. You got to check your work, so you're going to need to check, does x really equal negative 9/11? And when you check, you've got to get in the habit of substituting using parentheses, or things can get really weird. So I'm going to see if 7/3 of negative 9/11 increased by 1 does in fact equal twice negative 9/11. So I need two sets of parentheses there in the numerator of the fractional expression on the right hand side. One set of parentheses to enclose negative 9/11 and the other for the grouped quantity. You have to make sure you do that accurately. That's all being divided by 4, and I'm subtracting 2. And I am 100% going to use my calculator here because this is a little complex. So I'll have it evaluate the expressions for me. And I'm able to, I'll clear it out so you can see it better. Type in math. Just kidding. Hit alpha y equals. That'll get me my fraction key so that I can put 7/3 as the coefficient of the quantity negative 9/11, which you could put in as a fraction if you want, or you could write the fraction using division. That has to be increased by 1, and the expression on the left is equal to that nasty thing. Hey, that's a repeating decimal. I bet you that can be written as a fraction. The 1 at the end is the calculator just rounding. Math, turn it into a fraction. Okay, so negative 10/11 is the value of the expression on the left. You're not wrong if you said negative 0.90 repeating. We just don't, that's a little elementary. We don't really write it that way any longer. And for the expression on the right, I'm going to need a fraction bar. Alpha, F1, fraction bar. In the numerator, I have twice the grouped quantity, open parenthesis, for my fraction. If you want, you could put a fraction here. It's not necessary. You could write the fraction as division, but I'll put one there. Negative 9, scroll into the denominator, 11s. Scroll out, close off the substitution. add 3, close off the grouped quantity, scroll into the denominator, and then scroll out of the fraction to subtract 2 from that term. Yay! Negative 10 elevenths. How psyched are we? Yeah, negative 10 elevenths equals itself, and because when we evaluate the expressions with what we believe to be the solution to this relationship, the expression on the right is equal to the expression on the left, we know that we got it correct, that in fact x is equal to negative 9 elevenths. That is a non-integer. Don't call it an integer because there's a negative sign there. Integers are the whole numbers and their opposites. Rational solution. The integers do not include partial values, and that is clearly a partial value. And that's about as hard as it gets. And if you understand the concepts involved in there, technically you understand just about everything we've done this year, and you'll be in really good shape as we continue to work the next 2 weeks to get your grades to more appropriately represent how intelligent all of you are. That is the lesson on solving equations with solutions that come out to be non-integer rational quantities. I hope that it was a good review and that you're able to do a great job on the homework. Be well, everybody. Take care.